All right. May I ask if you could see the presentation? Anyone could give me a feedback on whether you can see my presentations or not? Oops. Great. Okay. So, all right, let's get started. Okay. Let me check whether my recording is on, just to make sure. All right. Okay. So what we're going to do today is to finish chapter 7 on cluster analysis. Well, I have to do this first. I have to stop my video. Okay. And then switch to this one. All right. Okay. So today we will finish chapter 7. And in this chapter, or in this lecture, we will continue with our discussions on a few clustering algorithms. And these algorithms are distance-based clustering, including k-means and k-medoids, and also hierarchical clustering. And then another algorithm that we would discuss would be dbSCAN. All right. Okay, so let's start with the k-means algorithm first. This is a partitional clustering approach. And each cluster is associated with a centroid or a center point. And each data object, let me call it X, is assigned to the clusters whose centroid is the closest to X. And in k-mean clustering, we have to specify K, which refers to the numbers of clusters that we want to group the objects into. And this values of K must be specified. And the basic algorithm is very simple. The outline of the k-means algorithm is just a few lines of code. So here, let me use an example to illustrate the ideas of k-means. So for example, if we have a numbers of objects, so every point here denote a particular object. All right, in let's say a two-dimensional space. Let's say this is this attribute A and this is another attribute B. You could have 3 or 4 or even higher dimensions, but the idea is the same. All right. So for the k-means algorithm, it works like this. First of all, given the values of K, which is the numbers of clusters that we want to group the objects into, we will first select K initial centroids. So for example, we randomly pick certain numbers of objects as the initial centroid. And in this example here, let's assume that K is equal to 3. That is to say, we want to group the objects into 3 clusters. So we randomly pick some centroid. For example, suppose we take this object as the initial centroid and this one as well, for example. All right. Then in the next step is just to perform a number of iterations. And in each iterations, we carry out 2 steps. And these 2 steps are called object assignments and centroid updates. Now, most of the computations fall within this object assignment steps. So here, let me explain it. So what we do is that we form K clusters by assigning all points to their closest centroids. What it means is that we go through the database, and for each object, we measure which centroid is the closest to it. And then we will assign the object to that particular centroid or the cluster that centroid represents. For example, suppose I have this object X here, right? And I need to assign it to a cluster. And how do I do that? Well, I measure its distance against the 3 centroid. And in this example here, clearly this centroid is the closest to X, and therefore we'll group X into the cluster represented by this centroid here. All right, as another example, suppose I consider this object Y, all right? And obviously this object is closest to this centroid compared to the other centroid, and therefore this object Y will also be included in this cluster represented by this centroid. And for this object, let's say Z, okay, it is closest to this particular centroid over the other, and therefore we'll group this object Z into the cluster as represented by the centroid. So this step here refers to, we go through every single object in the data set, and then we assign the object, let's say X, to a cluster whose centroid is the closest to it. So after all of these is done, then we'll have assigned all of the data objects in the database to some cluster, and that would finish the object assignment step. And after the object assignment step is done, for example, in this example here, perhaps all of this point will be grouped into this cluster, all of this point will be grouped into this cluster, all of this point will be grouped into this cluster. Then the second step would be the centroid update. That is, well, if we took a look of this cluster, for example, initially this is the centroid, which is the representative point of the cluster. But after the assignment step is done, we will update the centroid. We'll recompute the centroid. So for this particular cluster here, we'll consider all of the points in that cluster and compute a new centroid. So in this example, the new centroid probably would be a location that looks something like this here. All right. And then the k-mean clustering algorithm will repeat and so on. So we'll do another round of object assignment and then centroid update. After that, we'll do yet another round, so on and so forth. And these iterations continue until we do not see any changes to the centroid. So for example, for this cluster, the initial centroid is here, but after the first round, we will update the centroid to this location. So here in this example, we see that the centroid moved from the old locations to the new locations. And the k-means algorithm will stop if there are no movements of the centroid in a particular iterations, because in that case, that means all the clusters are very stable. There are no object changes, etc. So this is the basic k-means algorithm. Now here are some details of the k-means algorithm. Now, first of all, we noticed that the initial centroids are often chosen randomly. So what we said previously was that initially we have to pick k centroids to start the algorithm. And how do we pick those k centroids? Well, the typical practice would be just to pick those centroids randomly. However, we noticed that the final clustering result will depend on the choice of the initial centroid. That is, if we pick one set of initial centroid and start k-mean clustering, we get some clustering result. If we take another set of initial centroids, another set as the initial centroid, then we might get a different clustering result. So the final clustering result depends on the choice of the initial centroid. That's what I meant. All right. And when I say centroid, I'm talking about a representative point of a cluster. And this centroid typically is computed as the means of the points in a cluster. That is to say, we simply find the average, of the points within the cluster and use that average as the centroid. All right. Now, previously we said that in the object assignment step, every object X is assigned to the cluster whose centroid is the closest to it, right? So what do we mean by close? Closeness here could depend on the types of data, and this can be measured by using certain distance measure or similarity measure. For example, you can use Euclidean distance to measure the distance between two objects or 2 points. And the shorter the distance, the closer the two objects are. Or, for example, if every object in your data set, it's a document, then we may want to measure the similarity or closeness of two documents by using things like the cosine similarity. So this is your choice. But when we are doing k-means clustering, we have to prepare a similarity measure or a distance measure. And that similarity measure or distance measure is used to measure what we mean by closeness. So that is used when we are assigning the objects or points to the various cluster. So some more detail about k-means. We noticed that k-means usually would converge for common similarity measures, such as Euclidean distance. By converge, I mean that after several rounds, then the clustering will become stable. That is to say, the objects that are assigned to a certain cluster would not move or switch to another cluster later on. So the clustering become more stable. That's what I meant by convergence. And most of the convergence usually happens in the first few iterations. That is to say, the movements of the centroid usually happen the most in the first few iterations. And in the last few iterations of k-means, usually the movements of the centroid or the update of the centroids are very, very minor. And so the original k-means algorithm asks for a numbers of iterations until there are no changes to the centroid. But sometimes we might want to speed these things up by having an early stopping condition. For example, when we check that the centroid does not move much, if the movement of the centroids are very, very little in one iterations, then we consider the clustering is stable enough and that we can do an early stop. So that would save some computations. The complexities of the k-means algorithms is given by order n multiplied by k, multiplied by I, multiplied by d, where n is the numbers of objects or points in the data set. K is the numbers of clusters that we want to group the objects into. I is the numbers of iterations that we have to execute. And D is the numbers of attributes or the dimensions of the data. Now, let me explain a little bit why this is NKID. Now, if you look at the k-means algorithm, you notice that the most of the computations happens here in this line, which is the object assignment. This is the largest amount of computations that we have to perform. And in this object assignment, what do we need to do? Well, for each object, we have to assign it to a cluster. And so obviously, the algorithm would be proportional, the time taken by the algorithm will be proportional to n, which is the numbers of points, because in each iterations, we have to assign n objects to some cluster, right? And obviously, the computation will be proportional to the numbers of iterations that we have to perform, right? Because for each iteration, we have to do some amount of work. And if we have to iterate I times, then the amount of work will be proportional to I. And in each iterations, as I said, what we need to do is to assign the objects to some cluster. And in this assignment step, for each object X, we have to measure its closeness to the other centroid, all right, to the centroid of the various cluster. And that means that we have to measure several distances, right? Assuming these are the centroids of the various cluster. So how many such distance have to be computed? Well, it depends on the numbers of centroids that we have, which is equal to the numbers of cluster. So this is proportional to k. And measuring one distance, let's say if we are using Euclidean distance, obviously this distance computation would depend on the numbers of dimensions of the data objects. Higher dimensions, more you have to do to compute the distance, and therefore the computation is also proportional to the dimensions of the data as well. And so this is the complexity of k-means, all right? So some details about the k-means algorithm. Now, originally, I would like to show you an animation on how the cluster changes across iterations. However, as I said, I forgot to bring my computer. I cannot show the PowerPoint, and so there's no animations. The one that I'm showing here is a PDF file. So, but I'll try my best to explain. Now, here let's consider the following scenario. This figures here shows some points that we have, or data objects, and we would like to group them into, let's say, 3 clusters. So in this example here, we set k to 3. Now, if we look at this figure, if we look at this set of data, for the moment, let us ignore the color codes, all right? So every dot here represents a data object, and forget about the coloring, all right? And now if I ask you to group or to cluster these objects into 3 clusters, then if you eyeball it visually, we are likely to group these objects into one cluster, these objects into another cluster. You probably would group this object into a 3rd cluster, all right? So now let me color them based on our intuitions of how these objects should be clustered together, right? So we have the green group, the red group, and also the blue group. This looks ideal. This looks like an ideal clustering result that we might want an algorithm to help us figure out, okay? Now, So as I previously I said that if we apply k-mean clustering onto a set of data, we have to select an initial set of centroids. And the choice of this initial set of centroid might affect the final clustering result that you obtain. So here, let me show you two runs or two executions of the k-means algorithm. So this is one execution. This is another executions. Now, the difference between these two executions is that we used different set of initial centroid. All right. So for one particular set of initial centroid that we pick, we obtain this clustering result. Now, if you compare this result against what we thought would be, intuitively the best clustering, you see that they are very similar, right? Well, there are a couple of points that are not, they are not exactly the same. For example, for this point and this point, in this k-means execution, these two objects are grouped into the blue cluster. However, for our intuitions, we group these two objects into the green cluster. But this difference is very minor. But so, approximately this result of k-means clustering is very close to what we wish the data would be grouped, right? However, if we select another set of initial centroid, this is another execution's result that k-means obtained. In this particular example here, these objects are grouped into one cluster. These objects are grouped into another cluster, and we also have another group, which are colored the green. So if you compare this result against what we wish, what we thought intuitively should be the grouping, we see that this time k-mean doesn't do the job very well. All right. So again, the point that I would like to bring out is that the result of clustering depends on the initial set of centroids that k-means pick. So here, let me show you, let me show you the iterations for these two executions. Originally, I thought I could show you the PowerPoint, and so we have some animations, but again, we don't have the PPT here, and so let me see how I could explain this. All right, so let us consider, the set of objects first. All right, now in this example, because we want to do three means, because case 3, right? So first, we need to pick 3 initial centroid. And let's say, I'm not sure whether you can see it very clearly. I have 3 crosses, all right? So here is one, here is another, here is the third, all right? So we have picked 3 objects as the initial centroid. So the first initial centroid is here, the second initial centroid is here, the third initial centroid is here, all right? And now with k-means, we'll go through all of the objects in the data set, and we'll assign these objects to the cluster represented by the closest centroid. For example, if you consider this point, all right, and I compare its distance against the 3 centroid, we find that it is closest to this particular centroid over the other, and therefore this particular point here will be assigned to the blue cluster. All right. As another example, if you look at this point here, it is closer to the green centroid compared to the other, and therefore this object will be grouped into the green cluster. Okay. So after all of the data points are assigned to the cluster, this coloring shows the result of the first iteration. All right. So we have a numbers of objects grouped into the green cluster, a numbers of objects grouped into blue, and also some object grouped into the brown cluster. And this grouping is based on the 3 initial centroids that we chose, right? So after this object assignment step, the next step is to recompute or update the centroid. For example, if you consider the green cluster, these are the set of objects within the green cluster. So I would like to find the centroid of this group. Well, if you eyeball it, intuitively, I think the new centroid should be somewhere here, right? If I take the average of all the green objects. So it should be somewhere there, right? And in fact, this is the updated centroid for the green cluster. This is the updated centroid for the blue cluster. And that is the updated centroids of the brown cluster. And in the second iterations, we again do the same thing. We go through all of the data points and assign the data points to the cluster whose centroid is the closest to it. For example, if you consider, for example, let's say this point, right? Now, in the first iteration, it is assigned to the blue cluster. But in the second iteration, you see that this point is now closer to the brown cluster than to the blue cluster. And so in the second iterations, this particular object will switch cluster. Originally, in the first iteration, it was assigned to blue, but in the second iterations, because we have some updates of the centroid, this objects will now be assigned to the brown cluster. And in fact, if you look at this picture here, you show the resulting clustering after the second iterations. Compared to the first, you see some changes, right? Some of the objects has moved from one cluster to another. So after this clustering is done, then the next step again is to recompute or update the centroid. For example, if you consider the brown cluster here, this was the centroid. We for the second iterations, when we update the centroid, it seems that the centroid should move slightly lower, right? If I take the average of all the brown objects. So the updated centroid is now here for the brown cluster. The updated centroid for the green cluster is here, and that for the blue cluster is there. And then we continue, all right? So if you consider this steps across all the 6 iterations, and eventually, after about 6 iterations for this particular example, we have this result. And another round of object assignment, we find that there are no changes to the cluster. That is to say, there are no objects that would be switching from one cluster to another, and therefore we have a converged result. And at this point, the k-means algorithm will stop. All right, and this is the result of the clustering. So we have 1, 2, and 3 cluster as the result. So it looks good. All right. For this example here, it's kind of like the near optimal solutions. All right. However, if the choice of the initial centroid is different, we may have different results. So here, let me show you an example. All right. So suppose the first 3 centroids that we pick is this one, and that one. All right. Now, without going through all the details, again, you do object assignment, centroid update up in one iterations. In the second iteration, you do another round of object assignment, centroid update. If you go through these iterations, you'll find that in this example, if these are the 3 centroids that we pick initially, we will obtain this clustering result at the end. And this is not really optimal. In particular, these 2 clusters are incorrectly merged together to form one cluster. And also this big cluster, and also, this, let's see, okay. And this big cluster here is kind of like split into 2 by k-means. Right, so this clustering result is not as good as the one that we got in the previous example. Right, so what I'm trying to show is that depending on the initial set of centroid that you pick, k-means would give you a different clustering result. All right, so now the question is, then how shall we execute k-means, knowing that the clustering result obtained by k-mean could be suboptimal if we do not choose the initial set of centroids well. So typically what we do is that we'll run k-means multiple times, and then we will select the best clustering, all right? Because we know that sometimes k-mean may not be giving us very good clustering results. So we run it multiple times, and then we pick the clustering result or the run that gives us good clustering quality, all right? Now, then the next question is, how do we measure clustering quality then? Because if we said that we run k-means multiple times and then we choose the best one, right? But how do we measure, how do we quantify the quality of a clustering result? Well, there are a number of ways for measuring the quality of clustering. Here, let me show you just one first. This is a very common measure. This is the sum of square error. or SSE. Okay, so here's the idea. For each data point in the data set, the error is the distance to its cluster representative. So for example, let's say this is a particular cluster that we have found from our data. And let's say this point is the centroid of the cluster. And the centroid, as I said, is a representative point of the cluster. And we have multiple objects that are grouped into this cluster. Let's say one of them is called X. All right. So what we do is that, well, we imagine that if the values of X is replaced or approximated by the centroids of the cluster, then what would be the error in this representation? Well, the error can be measured by the distance between X and the centroid, right? And this is what we have here. So this is the distance. Now, given a cluster, let me call it Ci, for every object X inside the cluster, we measure this distance, where X is the point, and this Mi is the representative point for cluster Ci, for example, like the centroid. Okay, so we measure this distance, compute the square root of it, and sum it all up for all of the points within the cluster. So we use this distance, we find this distance, we find this distance, etc., square all of them, sum them all up, and this terms give us the SSE of cluster Ci. All right, and we have multiple clusters in the clustering result. In particular, we have K clusters, right? So we sum up all the SSE of all the K cluster, and that is the SSE, or the sum of square error, for a clustering result, right? So we run K-mean multiple times, and for each run, we'll obtain one clustering result, and then we compute the SSE for each clustering result, and the clustering results that give us the smallest SSE would be the best quality one, and that would be the one that we choose. All right, so given to clustering, we choose the one with the smaller SSE. So that's the idea. All right, and here I have a few more examples to illustrate, the K-mean clustering, and that the result depends on the initial set of centroid that we pick. So here we have a numbers of points illustrated. All right, in this example, and again, if you eyeball it visually, I see 10 clusters, and I color code them here, right? However, if I run K-means using a certain set of initial centroid, I may get different clustering results. So here in this example, because I'm doing like 10 means here, K is equal to 10, so I need 10 initial centroid. Let's say I got 2 initial centroids here. I get another 2 initial centroids here, another 2 initial centroid there, another 2 here, another 2 there. So in total, I get 10 initial centroids. Some of them are chosen from the same intuitive clusters. And after numbers of iterations, I get this as the K-means clustering result, which works fine, right? However, here's another example. Here's another example where the initial centroids that I picked was, I picked one centroid here, initial centroid here, another initial centroid here. That's another one. I got 2 here. I got another two here, one here, one here, and also 2 here, right? And if this is a set of initial centroid that I picked, after a few iterations, I see that this would be the clustering result given by K-means. And you can see this is not really optimal. For example, these 2 clusters are incorrectly grouped into the same cluster by K-means, and that this cluster is incorrectly split into 2 by K-means, right? I'm sorry, again, this picture is kind of small. You may not be able to read it very clearly. In my PPT file, I have the animations. Maybe I should put that PPT file onto Moodle so that you can see the animation better. Okay, but again, the point is just that the clustering result given by K-means depends on the choice of the initial centroid. And the way to get around this problem is that we could run k-mean multiple times and then choose the clustering result that gives us the best performance, the best quality. All right. So solution to the initial centroid problems, as I mentioned, we could do it multiple times and then select the clustering results that give us the smallest SSE, right? And there are some other approaches. For example, one approach would be let us do some heuristic when we're choosing the initial set of centroid. One heuristic would be to choose objects that are widely separated apart in the data set as the initial centroid. So when we are picking the initial centroid, we avoid picking objects that are very close together. So the idea is to avoid picking multiple centroids or initial centroid that belong to the same cluster. All right. And so this is one heuristic. Another way to avoid the initial centroid problem is to do what we call bisecting k-means. All right. So I will talk about bisecting k-means shortly. We will skip this slide. All right. So here is the bisector k-means algorithm. All right. This is a variant of the k-means algorithm. And bisecting k-mean produces a partitional or hierarchical clustering. So the idea here is that we start with one all-inclusive cluster. So initialize a list of clusters to contain just one cluster. And this cluster includes all the points. So all of the points in our data set is going to be in just one single cluster. And then we iterate. And in each iteration, this is what we do. We pick a cluster from the list of clusters that we have, all right, based on certain criteria, a point that I would come back shortly. So we pick a cluster, and then what we do is that we split it. We split that cluster, all right, into two, okay? And that's why this is called bisecting k-means. So we start with just one single cluster, which include all the points in the data set. And then in each iterations, we pick one cluster from our list of clusters, and then we split it into two. So how do we split it into two? Well, we simply run k-means, where k is set to 2. And that will split a cluster into two subcluster, all right? And then we can run it multiple times to see which two means, or k-means with k equal to 2, give us the best bisections. And then we'll take that as a result. And then we will add these two clusters back into the list of cluster, and then we repeat. Well, this is done until we obtain k cluster. So we start with just one cluster that include all of the objects. We pick one cluster and split it into two. So that would give us two clusters. And then we, again, iterate. We pick one of the two clusters to be split. The result of splitting that would give us 3 clusters in total, and so on and so forth. So until we get k cluster, and we'll stop, all right? So here, again, I wanted to show you an animations, but unfortunately, this is a PowerPoint. I couldn't show the PPT animations here, but let me just tell you very briefly how the bisecting k-means works, all right? Again, I will put the PPT file on Moodle after today's class so that you can take a look of the animations better, all right? So let's say I start again with these data points, right? But for the moment, forget about the color codes, all right? Forget about the crosses. There's no crosses. There are no color code, initially. So we have just one big cluster, all right? All of the objects is in one big cluster. Let me call it C1, all right? So with bisecting k-mean, what do we do? Well, we pick one cluster. Well, in this example here, when we start, we just have one cluster. So this would be the cluster that we pick. And we are doing and then we bisect it by calling k-means, where k is equal to 2, all right? So we run it multiple times to see how these objects could be grouped into two clusters. As I wanted to show in the animations, is that the result of these two means clustering will give you this partition. So all these objects will be clustered into one clusters. All these objects will be grouped into another cluster. All right, so that would be the result of bisecting k-means. So after this, we will have, let's say, this one cluster C1 here, and we have another cluster C2 here. All right. So in the next iterations, I have two clusters to choose from. I want to choose one of them to split. So whether I should choose C1 or C2? Well, there are many criteria for choosing a cluster to split. For example, we can measure the SSE of the clusters and see which cluster has the larger SSE. All right. The cluster that have the larger SSE would be picked to be split. For example, if you look at this C1 and C2, obviously C2 is a loser cluster. It's kind of like loser. I mean, the point more separated apart. And so probably this cluster C2 has a larger SSE. And so we may pick it and to split it. All right. For example, the result of this split might group these objects into one cluster and these objects into another cluster. And if that is the case, then after the split, we will have 3 clusters remaining. All right. And then we continue. We pick one cluster out of the 3 that has the largest SSE to split. And then we apply k-means where k equal to 2 to it to separate the objects in that cluster into 2 subclusters and so on. Now, in this example, k eventually is 10 because we want to group the objects into 10 eventual cluster. And so we'll repeat it a number of times until we get 10 clusters left. All right, so this is the basic ideas of bisecting k-means. All right. Okay, so here are some limitations of the k-means algorithm. First of all, k-means, well, it's a very common and popular clustering algorithms. We use it a lot. However, in certain situations, it doesn't give us very good results. In particular, if the data exhibit the following properties. First, like if the data form clusters that are of very different sizes, right, or of very different densities, or the clusters that the native clusters is kind of like non-globular shapes. In these cases, k-means doesn't give us very good clustering result. For example, for those data that exhibit clusters of different sizes and different density, we call this kind of data multi-scaled data. All right, so some data objects kind of like clustered very tightly together, so they have very high density. However, there are also data within the data set that are fairly spread out, right? And so in that case, the densities of the clusters, including those objects, will be very sparse. So in the same data set, if you find that in the same data set, you have clusters that are very dense, some clusters that are very sparse, then k-means may not be able to help you get those, obtain those clusters. Now, another disadvantage of our limitations of k-means is that it's susceptible to noise and outliers. Now, the reason is that every point under k-mean is assigned to a cluster. I mean, even outliers, if they're present in the data, would be assigned to some cluster. And for outliers, if they have some very extreme values, then when we are computing the centroid of a cluster, the presence of these outliers would distort the centroids of the cluster quite a bit. And that would make the clustering result not as ideal. And so that's what I meant by k-means are susceptible to noise and outliers. So here, let me show you some illustrations to further elaborate what I mean by clusters of different sizes, clusters of different densities, and non-globular shapes, and why, in these cases, k-means are not doing very well. So here are just some illustrations. Now, this is one example. Here we have a number of points, all right? Now, again, if you look at these data points, intuitively, you might want to group the objects into this blue cluster, the red cluster, and also the green cluster. Now, what you notice is that these 3 clusters are very different sizes. In particular, the red objects or the red cluster is much bigger than the other, okay? Now, you apply k-means. Let's say when you set k to 3 to this example data point, you probably would get this clustering result, all right? You notice that this big red cluster is incorrectly split by k-means into a number of fragments. So we run k-means on this data set, and we find that k-means give us this clustering result. All right. Okay. And again, this big red cluster is incidentally split into fragments, into subparts by k-means. Now, the reason why that happens is that this red cluster is fairly big. And so if you consider the centroid of this red cluster, probably this is where the centroid is, right? Now, if you consider this point, this data object, which is on the peripheral of this red cluster, well, you see that its distance from the centroid is quite far. The reason why we have this, fairly big distance is because this cluster is big, right? And so the object that is in the peripheral, that's kind of like the far edge of the cluster, could be at some distance from the centroid. And this example here, this distance is so big that this data point actually is closer to the centroid of the blue cluster. And that's why this object here is grouped into this cluster by k-means instead. All right, so this is one of the reasons. And here, let me show you another illustrations. Again, we have a number of points to be grouped into the cluster clustered. Intuitively, we think that these objects should be grouped into one cluster. These blue objects and green objects are grouped into other two clusters, right? If you run k-means on these data points, probably you will get this clustering result. In this case, again, the very large cluster, which has very low density, it's being split into two fragments. So there's one fragment, and here's another fragment. And also these two clusters, which has very high density, were incidentally grouped into one single cluster. All right. And so again, this shows, this kind of like illustrate that if your data is multi-scale, that means that the clusters that could be formed by the data could be of different density, could be of different sizes, then k-means may not be the best choice. And there are some special algorithm for clustering objects that can help avoid these multi-scale issues. But the details of those algorithms is a little bit more elaborate, and so we'll skip it here. Okay. All right. And here's another illustration showing the limitations of k-means. Now, again, we have a number of points that we want to group into cluster. Visually, we think that these blue objects and the red object should be grouped into two clusters. All right. However, we notice that k-mean is a distance-based clustering algorithm because the point is assigned to the closest centroid. And therefore, objects are clustered around certain centroids. And so the resulting clustering tends to be spherical in shape, all right? And therefore, for cluster that looks like these, which are not spherical in shape, would not be obtained by k-mean clustering. In fact, if you run k-mean clustering on this set of data points, this would be the result, all right? K-mean would group these objects into one cluster, and these objects would be in another cluster. So the cluster is more spherical, all right? So k-means is not suitable for discovering clusters of data points where these clusters actually not spherical in shape. Right? The reason why k-means give spherical clusters is because it's a distance-based clustering algorithm. All right. So those are the some of the discussions on k-means. All right. Now, another disadvantage of k-means is that again, if you give me a cluster discovered by k-means, well, we have a numbers of data objects within the clusters, right? And this cluster is represented by what we call a centroid, okay? And the centroid is typically the average of all the objects or all the points within the cluster. However, in some cases, in some application, if we measure or if we create a centroid based on averaging the data point, this averaging may not make much sense at all, particularly for categorical or binary attributes. So for example, if one of the attribute is, let's say, eye color, right? So you have eye color, like let's say brown or black or blue, etc. So how do you measure what do we mean by an average eye color? It doesn't make much sense, right? And also, if if the attribute is binary, let's say it's married or not, it's 0 or 1, yes or no, then what do you mean by an average of these binary attribute? Now, no one could be, for example, like 30% married, right? So in some cases, for categorical attribute, for binary attribute, it may not make much sense to find a centroid of a cluster by computing the average of the data points that are grouped into the cluster. All right. Now, in those situations, we might want to use, instead of centroid, we might want to use Madoy instead. And this is called the K-Madoy's algorithm. Now, the K-Madoy algorithms and K-means algorithm are exactly the same, except that for K-means, the centroid or the representative of a cluster is given by the centroid, which is the average of the data objects. But for K-Madoy's algorithm, the cluster representative is a Madoy of a cluster. I'll tell you what a Madoy is shortly. Now, a Madoy in a cluster C is a data object X and C such that the total distance from X to all of the other data objects is minimum. So first, we notice that a Madoy of a cluster C is a data object itself, all right? So this is not an average. It is itself a data object, all right? So it's kind of like a median, you know, of a set of numbers, all right, instead of an average, okay? So here, let me show you how do we compute the Madoys of a cluster. So here's a very simple example. Now consider I have a cluster with 4 data objects, x1, x3, x1, x2, x3, and x4, right? And let's say these data are 2-dimensional. We have 2 values, 2 attribute values for each data objects. Now, if I'm using centroid, which is an average of the data objects in the cluster, then what I need to do is simply compute the average of 0.3, 0.1, 0.5, and 0.4, and I get 0.325. I take the average of 0.6, 0.1, 0.3, and 0.1, I get an average of 0.0. Oops, sorry. I think this is a typo here. I get 0.275. All right, so this is the centroid, very easily computed. Okay. However, if I'm talking about Madoy, then as this is defined, the Madoy of the cluster is a data object within the cluster. And that data object is the one that is the closest to all the other data objects in the cluster. So here is how we find a Madoy of the cluster here. We consider x1, and what is the distances of x1 to the other data points, x2, x3, and x4? Well, this is the distances, all right? And then I sum all these distances. So what is the distance from x1 to x2? Well, I take this vector, and I compute the Euclidean distance. Okay, what is the distance between x1 and x3? I take this vector, and I compute the Euclidean distance, etc., etc. And I would get the sum of the distances from x1 to all other objects in the same cluster. In this example here, this sum is 1.41. I do the same thing for x2, x3, and x4, right? So in particular, for x3, the sum of distance from x3 to x1 to x2 to x4 is given by 1.032. So among all of the data objects within this cluster, we find that x3 has the smallest sum of distances to the other objects in the cluster, and therefore x3 is taken as the Madoy of the cluster. So one more time, a Madoy of a cluster is a data object within the cluster itself. And it is categorized as the data objects whose total distance to other data objects within the same cluster is the smallest. So in this example here, the Madoy of this cluster, it's given by 0.5, 0.3, which is the values of x3 here, all right? While the centroids of the cluster is given by these numbers, okay? So that's the Madoy definitions. All right. Okay. So the K-Madoy method, as I mentioned, is exactly the same as the K-means method, except that the representative used for a cluster is its Madoy, right, instead of its means or the centroid. And the K-Madoy's method, however, is much more computationally expensive than the k-means method. The reason is that computing the centroid is a lot easier than computing the madoid. Now, if you go back to the previous example here, how do we compute the centroid? It's easy. We take these four vectors and I compute an average, very easy. However, if we want to compute the madoids, there are so many distances that we have to compute, right? And then that will allow us to find which one is the madoid. So in particular, if you have a cluster that contains, let's say, m objects, all right, computing the centroid means that you have to take the average of these m objects. That is kind of like order m computations. However, if you want to find a madoid for each object within the cluster, you have to compute the distance to every other objects. All right, so every object pairs, you have to compute the distance, and so finding the madoid is order m squared. Right, so it's much more expensive. So researchers propose certain ways of doing k-madoids more efficiently. One of these algorithms is called PAM, or called partitioning around madoids. Right. Now the exact algorithm here is a bit complicated, and here what I just showed you is a overly simplified version. All right. I guess that what we need to know is just some basic idea. And if you are interested in the details, it's a whole, there are some research papers that you can read. So the PAM algorithm, or partitioning around madoid algorithm, goes like this. First, we pick k point in the clusters as madoid. So this is the initial madoids. Let me call this k point m1 to mk. All right, so we pick an initial set of madoids. And then we partition all the points into the cluster represented by the k-madoid. So this is basically object assignment, as I have previously discussed for the k-means algorithm. It's the same. All right, so we pick certain objects as the initial set of madoids, and then assign all the points, every single one of them, to a cluster based on which madoids is the closest to the object to be assigned. All right, so this is the object assignment step. So it's exactly the same as k-means. All right, and in the original papers of PAM, this step is called build. All right, and then the second step is called swap. All right, so what do? Well, we calculate an error. Right, so this is similar to SSE, but except that we do not square the distances. So basically, if you look at this term, this is just a sum of error of all the objects in a cluster CI. And this is the sum of all the cluster error. All right, so it's very similar to SSE, except that we do not square the distance, just the plain distance. Okay, so we call this the total error of the clustering. Now, the PAM algorithm would pick a point R in the data sets, and then it would replace a madoid MJ, right, that was previously selected by R. All right, so we attempt to kind of like replace a madoid by another object. And then we compute the error to see whether this replacement would result in a smaller error. And if so, we'll keep this replacement, and then we'll try another replacement. However, if we find that E is larger, that is to say this replacement doesn't reduce the error, then this replacement will be undue. All right, and we'll try to find another replacement and attempt that. And this is called the swap phase. All right, so we have a build phase and we have a swap phase. All right, now in the original PAM paper, it presented some strategies. In particular, it has a strategy for picking the initial madoids, and it also has a strategy for selecting a point R for the replacement, so that the whole process is more efficient. All right, but I would not go into details of that. If you're interested, you can look it up. There will be some details in the paper that you can consult. Okay, so that is the PAM. That is the PAM versions of the k-madoids algorithm. So that finishes our discussions on k-means and k-methods. I guess at this point, let us take a 5-minute break. And when we come back, we will talk about hierarchical clustering. So let's take 5 minutes and we'll resume at 10:31. All right, we are back. So I assume that you can hear me, right? Let's see. Just to make sure that I have the microphone on. All right, thank you very much. Actually, I had my COVID vaccine yesterday, and I'm feeling a little bit dizzy right now. Okay, so the next algorithm that we would like to discuss, it's hierarchical clustering. So here's the idea. Now with k-means or k-methods, we have to specify the values of k, that is the number of clusters that we would like to group the objects into. However, typically we do not know what the values of k is. We do not know how many clusters we should group the data objects into. So basically, the common practice is just do some trial and error. Based on your expert knowledge, you guess how many clusters that you want to group the objects into. And then you set the values of k, and then you run k-means. You take a look at the clustering result to see whether it makes sense or not. If not, then you adjust the values of k. So there's a lot of trial and error, and then you have to run k-means multiple times. Another alternative approach is to avoid having to specify a specific values of k, and this is called hierarchical clustering. So the ideas of hierarchical clustering is that we produce a set of nested cluster that is organized as a hierarchical tree, and this tree is called a dendrogram. All right, and a dendrogram is a tree-like diagram that record the sequence of merges and splits of the cluster. So here, let me use an illustration, use an example to illustrate. On the left here, what you see are some data objects, and they are illustrated as black dots. So we have 6 data objects. Object 1 is here, object 2 is here, object 3 is here, and so on. So we have 6 data objects. And then in this illustrations, you see some circle. And besides the circles, we have some label, and these are the merge step. So this, I have a red number 1 here, labeling this particular circle. This means that objects 1 and object 3 are the first pair to get merged into a cluster. And the second step of merging happens here, where we combine object 2 and object 5 into a cluster. The third step of merging is that we merge object 4 into the clusters of object 2 and 5, forming a larger cluster, and so on. All right, so this is how I interpret those figures on the right here. Okay, now this figures on the right, namely the merge steps and how the objects are being grouped into, can be represented, can be displayed as a dendrogram, which is shown here on the left. All right. So if you can still remember, in our previous meeting, I mentioned slightly about how the dendrograms are drawn. Now, first of all, on the x-axis in the dendrogram, we list all the objects ID. So, for example, in this illustration, we have 6 objects. So we have the ID of the 6 objects listed in the x-axis, in the horizontal axis. Now, we also have a vertical axis, and the vertical axis is displaying what we call the proximity of each merge, of the merges. Okay. Now, proximity can be expressed either by a distance or by a similarity measure. Okay. So you have to be very careful when you are reading a dendrogram, whether the vertical axis is representing distance or representing similarity. All right, the larger the distance of 2 objects, the less similar they are, right? the higher the similarity of two objects, the closer they are. So they're different. Okay. Now, basically, the vertical axis here showed a scale of proximity, and at the bottom, we say that we have very stringent proximity requirement. All right, and at the top, we have very loose proximity requirement. What do I mean? Well, at the bottom here, when we say we have very stringent requirement, we mean that the objects have to be very, very, very close or similar in order for us to put them into the same cluster. For loose requirement, for loose proximity requirement, I mean that, well, even those objects are somewhat apart, we can still group them into the same cluster. And that's what I mean by stringent requirement and loose requirement. Now, given that, if you look at this vertical scale, you see it's 0 here, right? And this numbers goes up, as we move from bottom to top. So in this example, do you think that the vertical axis, this scale here, represent distance, or does it represent similarity? Well, in this example, the vertical axis, the labels, the numbers here represent distance, all right? Why? Because at the bottom, we have distance 0, right? And as I said, at the bottoms of this dendrogram, it represents very stringent requirement, meaning that objects has to be extremely similar, extremely close, in order for us to put them into the same cluster. So what would be a most extreme stringent requirement is that the two objects have to be exactly the same for us to put them into the same cluster, right? So objects that are exactly the same means they have 0 distance. And that's why we see it's 0 here. So if you look at the dendrogram and if you look at the vertical axis and you see 0 at the bottom, this means the vertical scale is actually referring to distance. On the other hand, if the scale that you see on the dendrogram start with a 1 at the bottom and it decrease, right? And we have a 0 at the top, then this means this scale is representing similarity. At the bottom, objects have to be very, very similar. How similar? The similarity is 1.0. They are exactly the same in order for them to be put in the same cluster. So when you look at the dendrogram, check the vertical axis, and you have to, sometimes, as I said, the vertical axis represents similarity, sometimes it represents distance. So you have to be careful about that. Okay. So at the bottom of the dendrogram, as I said, we have very stringent similarity requirement. And so at the bottom, every object, it's a cluster by itself, all right? Nobody else is being grouped into the same cluster as the object, because we have very stringent requirement. We have objects that are exactly the same to be in the same cluster. So initially, every object is in a cluster by itself, all right? Now, as we move from the bottom upward on the proximity scale, we progressively loosen the proximity requirement. So at some point, we see that we start to do merge. That is to say, at some point, we start to allow objects to be grouped into the same cluster. If you look at these 6 data points here, you notice that objects 1 and object 3, these two objects are very close, are the closest pair, right? And so the first merge happens here, all right? We see that this is the distance between object 1 and object 3, all right? And how big is this distance? Well, object 1 and object 3 is merged at this distance, 0.05 unit, and therefore this is 0.05 units, all right? So the first merge happens here. So at this proximity requirement, if this is a requirement, if you draw a horizontal line across this dendrogram, you see 1 cluster, 2 cluster, 3, 4, and 5 cluster. So the intersections that you get illustrate or give you the set of clusters. Okay, so we have 5 clusters here. In particular, 1 and 3, objects 1 and 3 are merged into the same cluster. All right. Now, as we further loosen up the proximity requirement, we allowed further merging. In this example here, we see that objects 2 and 5 are fairly close. All right. And so the next merge happens among them. So we merge 2 and 5 together. to form a cluster. And this is the proximity or the distance between 2 and 5. All right. So if I draw a line, a horizontal line here, I have 1 intersection, 2 intersection, 3 intersections, and 4 intersections. So at this proximity or distance requirement, which is less stringent at the bottom, we have 4 clusters. The first clusters involve object 1, 3. The second clusters involve objects 2, 5. The third and the fourth clusters each involved object 4 and 6 respectively, right? So this is what I meant by the dendrogram. I hope that now you have a better idea of what a dendrogram means, okay? All right, so the strength of hierarchical clustering, as I said, we do not have to assume any particular numbers of clusters. That is to say, we do not have to specify the values of k as we need, as what we needed with k-means or k-mad-boy. Any desired numbers of cluster can be obtained by cutting the dendrogram at a proper level. So if you're given this dendrogram, all right, and if I want to obtain certain numbers of cluster, I set a particular proximity requirement and I draw a horizontal line. All right, so if this is the proximity requirement, I get 4 cluster. If I don't like 4 cluster, if I want more, I would have to increase or make the proximity requirement more stringent, right? So for example, I draw a line here, and I got 1, 2, 3, 4, 5 clusters. If I want fewer cluster, I loosen the proximity requirement. Let's say I draw a line here, right? Here I get 2 clusters. So given the dendrogram, I will be able to get different clustering result by adjusting the proximity requirement. So that is more flexible, okay? There are 2 main types of hierarchical clustering. They are called agglomerative clusterings and also divisive clustering. They work differently, kind of like the opposite to each other. The agglomerative clustering is a bottom-up approach. So we start with points as individual clusters, and at each step, we merge the closest pairs of clusters until we have only 1 cluster left. So this is kind of like what we just illustrated. We start with the bottom of the dendrogram. We'll try to build the dendrogram bottom up. So we start with each individual objects as a cluster by itself, and then we progressively loosen up the proximity requirement, and then we will do some merging, all right, at each step to get fewer and fewer clusters. So we start with 6 clusters in this case. We identify 1 merge, and that will give us 5 clusters, right? One less than previously. And we do another merge, and that will give us 4 clusters, right? So we identify all of these merge points from bottom to top of the dendrogram until we have just 1 cluster left. So this is agglomerative hierarchical clustering. The other one is called divisive. This is kind of like the opposite. We start with 1 all-inclusive cluster. So we only have 1 cluster that includes all the points. And at each step, we'll pick a cluster and we split it into 2. So this is kind of like bisecting k-means, right? Until it reaches the bottom of the dendrogram where we have each object being 1 cluster by itself, okay? So traditional hierarchical algorithm uses a similarity or distance matrix. And depending on whether you use agglomerative or divisive algorithm, we perform merging or splitting of 1 cluster at a time. So here, let me further illustrate agglomerative clustering. This is the most popular hierarchical clustering technique. The basic algorithm is extremely straightforward. So let me go through this very quickly. First, we compute a proximity matrix of the data objects. And then we let each data point to be clustered by itself. And then we iterate. We repeat the following step. We find out which 2 clusters are the closest among all the cluster pairs. And then we merge these 2 closest clusters. That would reduce the numbers of clusters by 1. And after this merge, we will have to update the proximity matrix. And then we will repeat this process until we have just 1 single cluster left. And the key operations in agglomerative clustering is the computations of the proximity matrix and how to choose which 2 clusters to merge, right? So let us elaborate on this point further. So this is an illustration of how we do you know, how the proximity matrix looks like and what we mean by merging. Okay, so in this illustrative example, we have 12 objects. Let me call them P1, P2 to P12. So at the bottom of the dendrogram, we have these 12 points. Now, of course, this is a toy example. In practice, you would have many, many more points for you to cluster. Let's say we have 12, all right? So first, we build a proximity matrix. Now, in this example here, this matrix will be 12 by 12. But again, this is a toy example. In practice, this matrix will be much bigger, all right? So for every pairs of points, you get a proximity value. And again, the proximity value can be expressed either using distance or using similarity. It's your choice, okay? All right, so, and then what we need to do is that we'll figure out, based on the proximity matrix, which pair of points has the strongest proximity, is the most similar, that is smallest distance or the largest similarity, and then we'll merge them, okay? And then after that, we will have to revise the proximity matrix and redo the same thing. So at some point, we might have already grouped the data objects into some numbers of cluster. So here is an illustration. Suppose the 12 objects have now, you know, after several iterations of the agglomerative algorithm, been grouped into 5 clusters. In particular, object P1 and P2 are grouped into one cluster, let's say C1. Object P3 and P4 are grouped into another cluster, let me call it C2, and so on, all right? So we have 5 clusters. And objects P10, 11, and 12 are grouped into yet another clusters. So we have 5 clusters. Now, the proximity matrix is a 5 by 5 matrix. Why 5 by 5? Because we have 5 clusters. If you have 4 clusters, the matrix will be 4 by 4, all right? So each entry here, let's say this one, represents a proximity value between 2 clusters. So this entry represents the proximity between C2 and C4, all right? Again, this proximity can be measured either by distance or by similarity. However, given 2 objects, we know how to measure the distance or the similarity. For example, we can measure the Euclidean distance between objects. But if you're giving me 2 clusters, and in each cluster there are some points in it, how do I measure the distance or the similarity between the 2 clusters, right? Because each one of them is a set instead of a single point. So for single point, I know how to measure the distance, but for sets, which are clusters, I don't know how to measure the distance. Now, there are actually multiple different ways for you to measure the similarity of the clusters. We'll get into that shortly. So let me continue with this example. So basically, after we have built a proximity matrix, we'll identify the clusters pairs that are the most similar, either in terms of the shorter distance or in terms of stronger similarity. For example, suppose we figure that C2 and C5 are the closest. They have the smaller distance among all the clusters pair. Then we will try to merge them, all right? And after the merge, we'll have 4 clusters left. They need this, and the merge cluster. So we have only 4 clusters left. And so we have to revise the proximity matrix and make it a 4 by 4 matrix and repeat, all right? So a while ago, I said that, well, given 2 clusters, we have to find a way to measure the proximity so that we can fill this proximity matrix, right? So how do we measure the proximity between 2 clusters? There are a number of alternatives, namely mean, max, group average, and also distance between centroids. So let us go through these different measures briefly, all right? The first one, it's mean, or sometimes people like to call it shortest distance, or sometimes people like to call it the strongest link, all right? So given 2 clusters, let's say we have a cluster C1 here and a cluster C2 here. The way, under mean, all right, the distance between these two clusters is given by the distance of the closest pairs of points between these 2 clusters. So this pairs of points represent the strongest link, the best similarity between a point in C1 and a point in C2. All right, so this is called mean. Okay, so this is one way. The other way is called max. You know, as the name suggests, I guess you can guess it. This is the largest distance between objects in the two clusters. All right. So in this illustrations here, we have C1 and C2, and this point pairs give the largest distance between a point in C1 and a point in C2. So this will be used to measure the distance between the two clusters under the max scheme. Okay. And for the other two are also quite intuitive. The third one is called group average. We measure all the distances of all the pairs of objects from C1 and C2, and then we compute an average. And finally, we have distance between centroids, or distance between average. So for the two clusters, C1 and C2, we first compute the centroids of each cluster, and the distance between these two clusters is measured by the distance between the two centroids. All right, and so these are 4 different ways for measuring the closeness or the proximity of two clusters. All right. So next, what I would like to do is to show you an example to illustrate how we actually build a dendrogram based on the similarity matrix, based on the proximity matrix. In this example here, let's say we have 5 objects. All right, just to make it simple. All right. Now, first we have to build a proximity matrix. Now, if you look at this proximity matrix, I said that proximity could be expressed either by distance or by a similarity. If you look at this table, actually what these numbers are similarity. You know, how can you tell whether these numbers are similarity or distances? Very simple. You look at the diagonal. All right. So in the diagonal here, we see 1.0, right? So what this value means, it means the proximity between the object 1 with itself, right? So this 1.0 has to be similarity instead of distance, because an object is exactly the same as itself, right? And so we have 1.0 here means that this is the similarity measure, right? If these numbers were distances, then for the diagonal, I should see 0, because the distance between an object with itself, it should be 0, right? And so for this proximity matrix I illustrated here, all these numbers represent similarity. Okay. All right. So first, we have 5 objects, and therefore I write the IDs of the objects at the bottoms of the dendrogram, and now I would like to build the dendrogram. All right. Now, suppose I'm using mean, all right, as the measure of the closeness between two clusters. Now, using mean, there is another term that refer to it. This is called single link clustering. All right. Sometimes people use the word single link clustering to refer to the mean approach. All right. So the similarity of two clusters is based on the 2 most similar or the closest points in the 2 different clusters. All right. So now, given the similarity matrix, we want to know what will be the first merge step. So which 2 objects will be merged first? Well, so we look at this similarity matrix, we'll see which 2 objects are the closest to each other, are the most similar to each other. So we observe that there is a 0.9 values here. And 0.9 is the largest one among all the numbers in this matrix, except for the diagonal, right? So this is 0.9, and it is between object 1 and object 2, right? So the similarity between object 1 and 2 is 0.9, and this is the strongest similarity among all the object pairs, and therefore the first merge point happens here between object 1 and object 2, and this should be 0.9 in terms of similarity, right? Okay, now next thing is that after 1 and 2 is merged, then instead of 5 cluster, we now have 4 cluster, and these 4 clusters are 1 and 2 form 1 cluster because we have already merged them. The object 3 form a cluster by itself. The object 4 form a cluster by itself. The object 5 form a cluster by itself, right? So now we have to convert the similarity of the proximity matrix or similarity matrix into a 4 by 4 matrix. In particular, I need to know what is the similarity between the cluster 1, 2 versus the cluster 3, right? Now, to know that, well, we take a look of this part. These are the similarity between objects 1, 2 and the object 3. Because we are using mean, right, or single link, we are considering the strongest link between the two clusters. So the strongest link between the cluster 1, 2 versus the cluster containing object 3 is 0.7, right? Where 0.1 and 0.7, the strongest similarity is 0.7. And therefore, the similarity between cluster 1, 2 and the cluster containing the object 3 would be 0.7, all right? And similarly, the similarity between the cluster 1, 2 and the cluster that contains the object 4 is given by these numbers, right? And we see 0.65 is the biggest, and therefore this is 0.65. Now this is based on mean, right? Because we are looking at the strongest link. So the strongest link between the cluster 1, 2 and the cluster 5 is 0.5, all right? And the similarity among 3, 4, 5 is given by this part of the matrix. So we have, all of these similarity numbers, and we also have these similarity numbers as well. So if you look at all these numbers, you see that the biggest one is 0.8. So the next merge point happens between 5 and object 4, right? And that's why in this dendrogram, the next merge would be to merge objects 4 and 5 into one cluster. And this refers to 0.8 in terms of the similarity. All right. So now, after this merge, we'll have 3 clusters, namely 1, 2 form a cluster, object 3 form a cluster, and 4, 5 form another cluster, right? So let's take a look of the distance between object 1, 2, and 3. Well, we have previously measured it. This is 0.7 based on the strongest link. Okay. What about 1, 2 versus 4, 5, these two clusters? What is the distance? What is the similarity between these two? Well, 1, 2, and 4, 5. So we look at this part of the matrix, and we find the strongest link. The strongest link is 0.65. And so the similarity between these two clusters under mean is 0.65. All right. And finally, the similarity between 3 and 4, 5 is given by this part. We find the strongest link, which is 0.4. So this is 0.4. Okay. So among these 3 similarity, this one is the strongest. So the next merge point happens between the cluster that contains 1, 2, and the cluster that contains 3, which is this merge point. And this merge point refers to the similarity of 0.7, and so on. Okay, so based on the similarity matrix, I illustrated how we build the dendrogram. Okay, so and this is under the mean scheme in measuring the cluster similarity. All right. In the next few slides, we have 2 more examples. One is based on the max definitions of cluster similarity. And well, for mean, we call the procedure single link clustering. But if you're using max, it is also known as complete link clustering. All right. Now, I'm not going to go through the details of how I built this dendrogram based on the max approach, based on the max similarity, cluster similarity measures. I will leave this as an exercise for you to try it out at home. All right. But if you compare the dendrogram, which is this one for max, versus the dendrogram that we obtained for mean, you see that the dendrograms are different. In particular, under the single link approach, the third merge points happen here between the clusters of 1, 2 and the clusters of 3. But for max, the third merge point happens here, which is between the clusters that contains 3 and the clusters that contains objects 4, 5. So different. All right. Now the next is using the group average to perform the dendrogram constructions, and this is the dendrogram that's being built. Again, I'll leave it as an exercise at home for you to see whether you will be able to build this dendrogram to test your understandings of the constructions algorithm. All right. Okay, so that finishes our discussions on agglomerative or hierarchical agglomerative clustering. Next, what we would like to discuss is yet another algorithm called DB-scan. Now, our discussions of DB-scan will be very brief because the exact algorithm is slightly complicated, but because of time, I will not be able to go through all the details. So I'll just tell you some of the concept or the basic concepts of DB-scan. And if you are interested, you can take a look at the book, the textbook for more details. Now, in the final examinations, there will not be any questions on DB-scan. All right, so don't worry so much about it. Let me just give you a brief descriptions of the algorithm. Okay, so DB-scan is a density-based algorithm, and the objective of DB-scan is to kind of like retrieve or identify clusters that are not globular or spherical in shape. So previously, I mentioned one of the weaknesses of k-means or k-medoids is that because they are distance-based, so the clusters that we obtained from k-means or k-medoids tends to be spherical in shape. But in some cases, the clusters that we want to obtain is not spherical. It's kind of like an elongated shapes, etc. And so we need to find some other ways to do it. And DB-scan is an algorithm that can help us retrieve or identify clusters that are not spherical in shape. Okay, we say that the DB-scan algorithm is a density-based algorithm. And so what do we mean by density? Well, density is the numbers of points of objects that is within a certain region, of a certain radius. And in the DB-scan algorithm, you have to specify a radius. This is called epsilon, all right? And given the data point x in the data set, the region surrounding x at an epsilon radius is called the epsilon neighborhood, or simply the neighborhood of the point x, all right? And what for DB-scan, well, objects or data points in your data set are classified into 3 types. And these are called core points, border points, and noise points. So here, let me tell you the definitions of what do we mean by core points or border points or noise points, all right? It's actually quite simple. Now, a point in your data set is a core point if it has more than a specified numbers of points given by a parameter, let me call mean points, all right, within its epsilon neighborhood. That is to say, if you give me an object x, right, I consider its epsilon neighborhood, all right, a kind of like a regions that is at a distance at most epsilon from it, and I count how many objects do I see in this neighborhood. And if the numbers of objects in this neighborhood is satisfy this min points requirement, then I say that this object is a core point, right? Okay, so that's simple. So within the neighborhood of x, if I see enough numbers of points, then I say that x is a core point. And by enough numbers of points, I mean that in this neighborhood, there should be at least mean points of objects that I would see. All right, so that's core point. Now, core points are points that are at the interior of a cluster. So they are within, kind of like the inside of a cluster. Within its neighborhoods, we see many friends, right? We see many other points that are similar to it. Now, what about border points? A border point, if I consider its neighborhood, it has fewer than min points. So they're not classified as core points. However, it is within the neighborhood of a core point. So again, a point is called a border point if itself is not a core point. That is, if I look at its epsilon neighborhood, I don't see enough points. However, the point is within the neighborhood of a core point. Then we'll call that point a border point. So for example, let's say x here is a core point, and let's say we have this object y here, all right? If I consider its epsilon neighborhood, I see very few points. So this object y is not a core point. However, it is within the neighborhood of a core point, then we say that y is a border point. All right. Now, as we will see later, as we'll discuss later, a border point would be assigned to the same cluster as the core point from which it is reached, right? Okay, now some more definitions. If a point Q in the epsilon neighborhood of a core point P, we say that Q is directly density reachable from P. So here, Q is within the neighborhood of a core point X, and therefore we say that Y is directly density reachable from X. And in notations, we write this, okay? Put an arrow, all right? X arrow Y means the object Y is directly density reachable from from X. That means that Y is within the epsilon neighborhoods of X, all right? Now, if a point Q is connected to a core point P through a path of directly density reachable points, that is, if P equal to some that is, if P2 is directly reachable from P1, P3 is directly reachable from P2, and so on, and Q is directly reachable from another point like Pn minus 1. So P and Q are kind of like linked together, are connected by a number of directly density reachable relations. Then we say that Q is density reachable from P. All right. Although this is not directly, but Q can be reached from P through a numbers of directly density reachable path. Then we say that Q is density reachable from P. All right. And a noise point is any point that is not a core point and this is not a border point. That is, a point Z is a noise point if within its neighborhood, I don't see enough numbers of points. So this is not core. And it is also not in the neighborhood of any core point. So this is not border. And those points are called noise points. And noise point will not be included into any cluster result, all right, by dbScan. Okay. So here it's the illustrations of noise points, core points, and border points. So in this example here, let's say we have the mean point requirements of 4. And if you look at this point here, if I look at this circle, which represent the neighborhood of this point, we see that we have 1, 2, 3, 4, 5, 6 points, which is enough. And so this point is a core point, all right? Now this point here, if I consider its neighborhood, I see only 1, 2, 3, 3 neighbors, which is not enough. And therefore this point is not a core point. However, this point is within the neighborhood of a core point, and therefore this is a border point. Now, if you look at this point here, if you look at its epsilon neighborhood, I only count 2 points, all right? There are only 2 neighbors. It's not enough, so it is not a core point, but it is also not within the epsilon neighborhood of any core point, and so this point is a noise point, all right? So in the next slide, this is kind of like the details of the dbScan algorithm. I am not going to go into this detail, but if you are interested, you can read about it at home and probably by the textbook. But basically, the idea here is that, well, instead of going through this this few bullets, let me just tell you the basic idea. The basic idea here is that I classify all the points as core, border, and noise, right? Noise points is easy. We ignore them. They are not included in any clusters, all right? Core points, if they are connected together by the density reachability relations, so all core points that are connected by the density reachability relations, all of these core points will form one cluster, all right? And also, the border points that are reachable from the core, for some, by definition, a border point is a point that is reachable from a core point. And the cluster label of a border point depends on the cluster label of the core point from which the border point is reached. So that is the basic ideas of how we label the points by giving them clusters ID. All right, so noise point is not included. A core point form the core of a clusters, and the border points that are reachable by some of the core will be given the same cluster label as the core points. All right, so here it's the properties. Noise point are not included in any cluster. Core points that are connected by density reachability form a cluster, and a border point A is assigned to the cluster that contains a point P such that A is density reachable from B. All right, so that's the basic ideas of DBSCAN. So here, let me show you some experimental results, of DBSCAN, illustrating how DBSCAN work. So let's say this is a set of points that we want to cluster. Now, if you look at these points, visually, it consists of a number of clusters. For example, this kind of look like a cluster, right? This is kind of like in other clusters of points, etc. So some of these the point clusters kind of like U-shaped. They're not spherical in shape, and so it is very, very difficult for k-means or k-methods to identify the clusters as possible. All right. However, if we apply DBSCANs onto it, let's see what would be the clustering results. Now, first, DBSCAN will classify all these points as either core, border, or noise. And let me color code the points here to illustrate. So all the points that I color green are the core points. Points that I color blue are the border points. And those that I color red are the noise points. So you see that most of these within the clusters, they're the green points, the core points, and the border point are kind of like on the peripheral of the cluster. All right, and here let me show you the resulting clustering, and I color code the clusters, so objects that are in the same cluster are given the same color, and also we have some black points here. These are the noise points, and these noise points are not included in any cluster. So you can see that the DBSCAN algorithm is able to determine clusters that are not spherical in shape. All right. Okay. So far, what we have discussed, it's a number of clustering algorithms. We talk about k-means, k-methods. We talk about agglomerative hierarchical clustering. We talk about how to build dendrogram. We talk about the DBSCAN algorithm. And then the final, we have just a few more slides. So here we want to discuss a little bit about how we measure clustering quality. All right. So previously, we said that how we could measure the quality of a clustering is that we could do SSE. We can compute the sum of the square of the errors to measure the cluster quality, right? However, if you think about it, SSE alone is not quite enough. Now, the reason is that the clustering principle is that we want to group objects into different clusters such that we have very small or relatively small intra-cluster distances, right? And we want large inter-cluster distances, right? The reason why we want this is that if we have small intra-cluster distance, it means that objects that are put into the same cluster are very similar among themselves. If we have large inter-cluster distances, it means that objects that we put into different clusters are quite far apart, right? So that would be the ideal situation of clustering. We want small intra-cluster distances. We want large inter-cluster distances. But if you think about it, when we talk about SSE, we're saying that, well, you give me a cluster, let's say CI. I have a centroid, and we have some objects within the cluster. And SSE basically measure the distance between an object in the cluster to the centroid of this cluster. In some sense, SSE is measuring just the intra-cluster distances. So how tightly the objects in a cluster are among themselves, all right? SSE doesn't give us any clue about the inter-cluster distances. So there's some limitation, all right? Now, in terms of measuring clustering quality, there are two concepts. One is called cohesions, which is the average intra-cluster distance, and also separations, which is the average inter-cluster distances. And SSE, in a way, is kind of like measuring cohesions only. So we want to have ways of figuring out the separations of the clusters in measuring the quality of clusters. Right? So one way to do it is called the silhouette coefficient. Right? So here, let me give you a brief idea of what the silhouette coefficient is about. Now, the silhouette coefficient combines the ideas of both cohesions and separations. And for an individual point I, all right, we calculate two numbers. Let me call them A and B, all right? So for example, this point is point I, okay? So what do we do? Well, we calculate two numbers, A and B. What is A? A is the average distance of I to the points in its cluster, all right? So I have some other objects in the cluster. I compute the distance between the object I against these other objects. I take an average. That is the values of A. All right, so this is the average intra-cluster distance of the cluster that contains the object I. All right. In addition to A, I calculate another number. Let me call it B. B is the minimum of the average distance of I to the points in another cluster. So for example, if object I is in cluster C1, and let's say there is another cluster, let me call it C2. I have some objects in this cluster. I measure the distance between I and these objects, and the average of them. Let me call this let me call this C. Let me call this C1. Okay, and the average of this inter-cluster distance between I and the objects in the cluster C1. Let me call it B1. All right. So let's say I have another cluster. Let me call it C2, and I measure the same. Right. I measure the inter-cluster distance from I to this object. I take the average, and let me call that average B2, and so on, right? So I consider all of the BIs, and I check which one is the smallest, and that smallest one is the B value of the object I. So essentially, B is the average distance of I from the objects in another cluster that is the closest to I. All right. Okay. So after we obtain these numbers A and B for this object I, then the silhouette coefficients of this point I is given by this formula, which is 1 minus A over B. All right. And now if you think about it, if we have for very ideal clustering, we want intra-cluster distance to be small. That is, we want A to be a small value, right? And for ideal clustering, we want there is enough separation between object I and the other clusters. And so we want the values of B to be large, right? So a small A and a large B mean small intra-cluster distance and a large inter-cluster distance. So that would be good clustering. And if we have small A and large B, this ratio will be small, and 1 minus this ratio will be closer to 1. So a silhouette coefficient of closer to 1 would be a good indication, would be indications of good clustering, right? So what we can do here is that we calculate the silhouette coefficients for every single data point that we have in the data set, and we take an average. And that would be the average silhouette coefficient, and that would be an indication of how good the clustering result is. Okay, so next, another way of kind of like measuring the clustering quality is pretty interesting. This is not one quantitative measure. This is to check, the clustering result visually. And sometimes people like to do this. So what we do here is that we can color code the similarity matrix of the objects, and from this visualizations, we'll be able to tell whether the clustering results is good or not. So here, let me tell you what we are doing. So for example, suppose we have this data set, we have a numbers of data objects. If you look at these data objects, let's say I apply k-means or k-medoids, whatever algorithm that I use. Let's say the clustering result indicate these 3 clusters. All right. For example, suppose I have 100 points in my data set. Then I built a similarity matrix, and this similarity matrix would be 100 by 100, right? Because I have 100 objects here. So every entry in this matrix gives me the similarity value between a pairs of objects, all right? So what I would do in with this similarity matrix is that based on the clustering results, I grouped and ordered the points so that points that are grouped into the same cluster are located in the similarity matrix together, all right? So for example, if I call these clusters C1, C2, and C3, then I put all of these objects in C1 here in the kind of like the first segments of the matrix, all right? And then I order all the objects in C2 here, and then I ordered all the objects in the cluster C3 here. Likewise, for the vertical scale, all right? Okay, and then I would create this similarity matrix, and I would visualize the values in this similarity matrix using some color code. For example, I use blue to represent very low similarity. I use red to represent very high similarity, right? Okay, and then I can visually look at the values of the similarity matrix by observing the coloring. Now, if you take a look of this similarity matrix, you'll find that this indicates very, very good clustering because this similarity matrix is visually very crisp, right? We see clear rectangular or square regions where we see strong patches of red colors. So for example, what does this region represent? This region represents the similarity between the objects within the cluster C1. And if you look at this region, you see mostly strong red, very bright red colors. So that means that the objects that are put into the cluster C1, they are very similar among themselves. They have very strong similarity, right? Likewise, for these for this square here and for this square here, we see bright red, right? Very strong similarity among the objects within their assigned cluster. Now, if we look at this region, right, what does this region represent? This region represents the similarity between objects from C1 to those objects in C3. So these regions are displaying some inter-cluster distances or inter-cluster similarity between the objects in C1 and the objects in C3. And within this region, you see mostly very dark blue. That means that these inter-cluster similarities are very, very low. And so visually, this similarity matrix tells us that this clustering result is very good because we see very crisp images of certain clearly red diagonal regions, while the non-diagonal regions are all very blue, right? So here, let me show you another example. So this is the points that we have. And let's say the clustering result looks something like this. All right. Now you see that in this example here, the points are more scattered across, and there's no clear indications of clusters. So what is the quality of this clustering? Well, if you look at the color-coded similarity matrix, you see this. Now, in this example, this is in sharp contrast to the one that we had in this example. For this example, we see very crisp image. But for this example here, we don't see a very crisp regions. So this is the diagonal regions. These are the diagonal regions. Well, although you see that these are quite red, however, within this diagonal region, you also see patches of non-red pixel, right? So here, if you look at this region here, we see some blue and green values of pixel. So that indicates fairly low similarity. That means that within the same cluster, we do have some weak similarity within for objects that are put into the same cluster. So this means weak cohesion. And also for the non-diagonal region, let's say this one or this one, you see some red too. So that means that there are, in terms of the inter-cluster similarity, you see some strong links as well. So there is not enough separation. And so by visually observing the similarity matrix, by color coding the similarity matrix, this is another way that we can kind of like tell the quality of the clustering. So this is something that sometimes people would do just to kind of like a data visualization method. Okay, so I guess this is what I would like to say for this chapter. And let's see. Right, so that's it for the the extra lesson. And again, I would like to thank you all for attending this extra lecture. If you do have any, okay, so I got a question, so let me take a very quick look at that questions. Oh, I see some messages in the chat room, because while I was presenting the slides, I couldn't quite look at the chat room. So let me take a look at it. Most widely separate options components. Not quite sure if I understand. Okay, so one question is whether k-methods solve any limitations that k-means has. Well, the k-methods are not. It solves one limitations of k-means, which is that each represent that. I mean, for each cluster, the cluster is represented by a centroid under k-means, but that centroid is not a real data object, and so in some cases the centroid doesn't make sense because the centroid is basically average. As I mentioned, if one of the dimensions is like eye color, then it doesn't make sense to talk about an average eye color. If the attribute is like whether a person is married or not, it's a binary attribute, it doesn't make sense to say someone is like 30% married. So the k-methods try to solve this problem. That is to say, the representative of a cluster using methoid in some application makes more sense. Another question is, can we talk about most widely separated objects in K4? I don't quite understand the questions. That questions. Okay, so let me take a look of another questions. Can you go through the B parameter in the silhouette coefficients again? Sure. So let's see if I can share my screen again. All right. So the silhouette coefficients, this has two numbers, A and B, right? So the values of B is computed like this. So let's say I have this object being the object I, and let's say this is cluster C. And in the clustering result, we could have other clusters. So let's say this is cluster C1. Maybe we have another cluster, cluster C2. Maybe we have yet another cluster, let's say cluster C3, right? So how do I compute B for this object I? Is that I would consider the distance from I to all the objects in C1. All right, so we have, let's say we have three objects in C1. We compute these three distances, and the average will give me a B value. Let me call it B1. All right, and let's say C2 has another four objects. So I measure the distance between the object I and the objects in C2, right? Take the average, and that will give me a number, let's say B2, all right? Let's say C3, there are two objects, and I measure the distance to those, take the average, and get another B, let's say B3, right? So now I have one B for each cluster other than the one that I is located. I consider these B's and see which one is the smallest, and the smallest one would be the actual values of B given to the object I. All right. So in a sense, if you think that like B1 is the smallest again, among B1, B2, and B3, it means that this cluster is the one that is closest to the object I. And I want to know what is the average inter-cluster distance from the object I to this closest cluster. And that is captured by this value B here, right? So that's the silhouette coefficient. I hope that this is clearer. All right. Okay, can we talk about the bisecting k-means and give an example? It's not easy for me to illustrate because I don't have the PowerPoint here, but let me use a whiteboard to, I'll try, okay? Let's see if I can. All right, let me find some space for the bisecting k-means. The bisecting k-mean actually is quite simple in terms of its idea. So let me very quickly go back to the slide where I talked about bisecting k-means. All right. How could I? So let me try it again. Oops. Let me clear this slide first. All right. Now, suppose I have this point to be a cluster. First of all, ignore all the color code, ignore all the crosses that I have here. Just assume that I have a whole bunch of points that I would like to group into 10 clusters. All right, because now k is equal to 10. All right, I want to group them into 10 clusters using bisecting k-means. So first, I consider all of the points to be in one single cluster. Let me call it C. All right. And for bisecting k-means, what I simply do is that I'll take a cluster, try to split it into two. So in the beginning, we only have one cluster. And so our objective is to split this cluster into two. So I have so many points here. How do I split this cluster into two? Well, I would run two means, right? It's not a very good name because it sounds like it sounds like two means, right? So I'm running k-mean with k equal to 2. That is to say, I would randomly select two objects as the initial centroid. I go through all of the objects and assign these objects into one of the two initial centroid to form two clusters. Now, in this example, if you go through, if I could show the animation, you'll find that if I use two means to bisect this cluster C, this would be the result. I would group these objects into one cluster, and I will group these objects into another cluster, right? So let me call these two clusters C1 and C2. Now we have two clusters, right? But we cannot stop here because we need 10 clusters at the end. Now we have two clusters only, all right? So in the next iterations, again, I would need to choose one cluster and split it into two. So the point is, shall I choose C1 to split or shall I choose C2 to split? Well, the choice of a cluster to split could be dependent on many factors. One possibility is that we can select the cluster with the largest SSE to split, all right? So if you look at these two clusters, C1 and C2, which one do you think has the largest SSE? Do you remember what the SSE is? Well, for this cluster, let's say C1, I find its centroid. So that's the average of all of these points here. Well, let's say the centroid of C1 is here. Let's say the centroids of C2 is here, right? So what is the SSE for the cluster C1? Well, I measure the distance of all the objects against the centroid, right? Square these distances, sum them, etc., etc. So because the objects in a C1 is more spread out, so intuitively C1 has a larger SSE, right? And so then compared to C2, so pick C1 to split. So how do we split C1? Again, we applied two means, right, to group the objects in C1 into two clusters. Right? So if you run this algorithms onto the objects in C1, you'll find that the resulting clustering will look something like this. All right, so let's say we have a Let's say we have a C1, we have a C2, and a C3. Now we have 3 clusters. Again, we cannot stop yet because we need 10 clusters. So again, we need to find a cluster to split. So we have 3 choices, C1, C2, or C3. We can compute its clusters according to the SSD, pick the cluster with the largest SSD, and split using 2 means. So we keep on doing this until we get 10 clusters as a result. So that's the idea. I hope that this is clearer. Okay, another question is, when we calculate the silhouette coefficient, we choose the individual point randomly? No, the answer is the silhouette coefficient is defined for each individual point. And if we want to find the overall clustering quality, we have to compute the silhouette coefficient for all the points. And then we take the average. But if you think that that is very computationally expensive, you can do some sampling. That can also be done. But basically, what you do is that you compute the silhouette coefficient for all the points and compute the average silhouette coefficient. Okay? All right. So if there isn't additional questions, then I guess that will be it for today. I would like to thank. Oops. I would like to thank you for joining us in this meeting, and yeah, and good luck to your exam. All right. If you do have any additional questions, you can post it on Voodoo, and we will try our best to answer your questions. All right. Thank you very much, and I will see you later. Okay. Bye bye. Thank you all.